All right, let's talk about a problem that's absolutely everywhere, hiding in plain sight. It's at the heart of the internet, our power grids, road networks, you name it. The question is, what is the absolute cheapest, most efficient way to connect everything? To get our heads around this, imagine this challenge. You've got a map of a country with a bunch of cities. You also know exactly how much it costs to build a road between any two of them. Your job? Connect every single city, but do it for the lowest possible price. And here's the kicker. No pointless loops. You can't have a road that just takes you back where you started without visiting a new city. It sounds like a brain teaser, right?
Well, the solution is actually beautiful. It's not some one-off trick. It's a really powerful idea from computer science called the minimum spanning tree. This is the elegant mathematical answer to this exact kind of problem.
So let's dive in. We're going to break down what a minimum spanning tree, or MST for short, really is and why it's so critical to, well, how we've built our modern world. Okay, that definitely sounds like it was ripped straight out of a textbook, so let's translate that into plain English. You start with a graph, which is just a fancy word for a bunch of points, or vertices, connected by lines or edges. The MST is just a selection of those lines. You pick just enough of them to connect all the points together with absolutely no loops, and, this is the most important part, the total cost of all the lines you picked is the lowest it can possibly be. And believe me, this isn't just some abstract theory. This is the invisible blueprint for so much around us. We're talking about laying down those massive undersea internet cables, designing power grids to be as efficient as possible, and even in artificial intelligence for clustering data. This concept is, quite literally, everywhere. But hold on. Before we can just start finding an MST, our network, our graph, has to play by a few simple rules. You can't just throw this at any old diagram and expect it to work.
Yeah, there are three non-negotiables here. First, the graph has to be connected. That just means there's already some kind of path to get from any point to any other point. Second, it has to be undirected. Think of the connections as two-way streets. You can go from A to B and B to A. And third, it's got to be weighted. Every single connection needs to have a cost or a distance or some kind of value attached to it. So here's a really crucial piece of the puzzle, the spanning tree part. A spanning tree is basically the leanest possible skeleton for a network. And here's the magic rule. If you have V cities, you will always use exactly V-1 roads to connect them all without any loops. It's a perfect formula.
So, the million-dollar question, how do we actually find this minimum cost tree? Well, let's meet our first method, Kruskal's algorithm. The best way to think about this one is as the ultimate bargain hunter. It looks at the entire map at once and just goes for the cheapest deals first. The logic here is just brilliantly simple. First, you take every single possible connection you could make and you sort them in a list, from the cheapest to the most expensive. Then, you just start at the top of the list. You pick the cheapest option. The only question you ask is, does adding this road create a pointless loop with the ones I've already picked? If the answer is no, you keep it. If yes, you toss it and move to the next cheapest. You just keep doing that until you've got your V-1 connections. That's it. Now, for you performance nerds out there, the efficiency here is described as O of E log E. So what does that mean? It basically tells us how the algorithm's runtime scales as the number of edges, or roads, grows. That log E part comes from that very first step, sorting all the possible edges by cost. That's actually the most work the algorithm has to do. You might be wondering, how does it know if adding an edge creates a cycle? That's not magic. It's a super clever data structure called a Disjoint Set Union, or DSU. You can think of it like a super efficient bookkeeper that keeps track of which cities are already part of the same connected group. It's the secret weapon that lets it instantly spot a redundant connection. Okay, now let's flip the script and look at a totally different way of thinking. If Kruskal's is the global bargain hunter, then Prim's algorithm is more like a cautious explorer. It starts in one spot and carefully grows its network outwards, one step at a time. Prim's approach is completely different. You just pick any city on the map, it doesn't matter which one, and start there. Then you look at all the possible roads leading out from the network you've built so far. You find the single cheapest one that connects to a new city, one you haven't visited yet. You add that road and that city to your growing tree, and you just repeat that process. Find the next cheapest connection to a new place, and you're done when every city is connected.
To do this efficiently, Prims uses a couple of key tools. It uses something called a min-heap, which is basically a smart to-do list that always keeps the cheapest available road right at the top, ready to be grabbed. And it uses a simple visited list, just to keep track of which cities are already part of the tree so it doesn't go backwards.
And what about its performance? Well, using that clever min-heap, Prim's comes in at O of E log V. Now, notice the difference. Its speed depends on the logarithm of the vertices, V, not the edges, E, like Kruskal's. And that little change is exactly what makes one algorithm better than the other in different situations.
All right, so we've got two incredibly powerful and elegant ways to solve the same problem. So, which one do you use? Which one's better? It's time for a little showdown.
This table really sums it up. Kruskal's, because it sorts all the edges up front, tends to be better for what we call sparse graphs. That's a network where you have lots of cities, but relatively few connections between them. Prim's, on the other front, often wins out in dense graphs, where everything is highly interconnected. At their core, their logic is just different. One is global, the other is local. And hey, just a friendly piece of advice if you're going to try this yourself. There are a few common tripwires. Remember, this whole thing only works for undirected, two-way street kind of graphs. And if you're using Kruskal's, you absolutely cannot forget to check for cycles. And with Prim's, forgetting that visited check is a fatal flaw. Get those wrong, and you won't find the minimum cost. And here's a really interesting little fact. Is the final network you build always going to look the same? Well, no, not always. The final cost will always be the lowest possible for sure. But if you have two or more potential roads that have the exact same cost, you could actually end up with several different looking networks that are all equally cheap. So after all that, what's the big takeaway here? You've basically just been handed a network building superpower. And it's all built on two different but equally powerful philosophies. You can really boil it all down to this. Kruskal's algorithm is what we call edge greedy. It's obsessed with the edges. It just wants to find the absolute cheapest connection anywhere on the map, period. Prim's algorithm, on the other hand, is node greedy. It's focused on the nodes, on the cities. It just wants to expand its known territory by taking the cheapest possible next step. Two different kinds of greedy, same optimal result. And that, I think, teaches us a really important lesson about optimization in general. The cheapest, most efficient path is almost never the one that looks the most obvious at first glance. It takes a systematic, greedy strategy to uncover it. So I'll leave you with this thought. What complex network in your world are you going to optimize next?